Good afternoon, everybody. So we are going to start some new topics this week. So let's commence. So before that, yeah, okay. I think good amount of you are already here. So let's start. Okay, so I hope you can see my screen. So there are a couple of announcements I would like to make. So the first thing is there are 2 weeks to midterm. So midterm, the exact date of midterm will be announced by the academic office, but there are 2 weeks. But there are two deadlines that you must keep your mind. I mean, you should know about that. Anyway, you would have seen. Assignment 2 is due March 6. Okay. And assignment 3 is due March 14th. Okay, so these things will take time. I hope you have already started on this. Unfortunately, I cannot extend any of these things because there will be more assignments that you need to do. Anyway, there are a lot of choices. This is a group assignment. This one is individual, but there are a lot of things that you could do. So, I mean, many choices are there. So that way, for at least undergraduate students, they should be okay. Yeah, so there are these assignments that are due, and in the final exam, in the past when I did a final exam, I had a coding component, but this time I will not keep it because it doesn't make sense to code under a deadline. So yeah, so otherwise the exact format I will announce next week. So I'm also planning to, like 2 weeks before your final exam, I think the midterm week. Okay, so I meant there is no coding component in the midterm, and I will also announce the format of the midterm next week. The midterm week, I think, is March 15th, the week that starts on March 15th. And yeah, so I will try to cancel a couple of classes before this. Okay, so since we have been having one extra regular class every week, before midterm and final, I can cancel a few of these classes so that you can have more time to read. So I will do that. I will tell you exactly how many classes I will cancel so that you can read. Yeah, and what else? Yeah, so the format I will announce next week. Okay, the syllabus will be all that we will be doing, including the next topic, which is linear models. So we will cover cover a couple of easy topics on linear models this week and beginning of the next week. So those things are also part of the syllabus. Yeah. So anyway, so let's get started. So today we are going to talk about linear models or linear discriminant classifiers, linear models. Okay, so that's what we are going to start. But before that, I would like to review some of the things that you may or may not already know. So any case, so this should be useful. Are there any questions or comments? So we will review some linear algebra, some vectors, okay, then concepts like hyperplanes, all these things we are going to see. So these things many of you have already seen, but the main thing is we need to use this in our linear models discussion. This is going to come very often. So that is why I am going to talk about this. Okay. So one of the things that you have already learned in your 12th standard and other places is that there are two views that you have been taught of, right? So one is Cartesian coordinates. So you have this Cartesian coordinates, right? So what you have is this axis xy, possibly even z axis could be there. Okay, and then every point you are characterizing as the x coordinate, y coordinate, and maybe if you are talking about 3 dimensions, then z coordinate also is a part of it. So this is one view. This is the view that you would have studied in your analytical geometry and things like that. Okay. Okay. So the other view that you would have seen in physics and other things is that you have you are thinking of a vector as a thing that has magnitude and direction. Okay. So the same point xy, okay, is represented as a vector which is having this direction and this magnitude. Okay, so the thing that you have also learned when you learned vectors is that you can translate this vector anywhere, provided it is of the same magnitude and same direction. Suppose this is x, so this is the vector x, so this is also the vector x. Perhaps I should not call it x because I have already used x here. So if I call this vector u, this is the same vector because the length is the same and the direction is same. I mean, I may not have written it properly, but this is what you would have seen. Okay, and the length of a vector. So these two views, like Cartesian coordinates as well as this vector view, they are quite related. Okay, so the length. So if I am having, this is the 0, 0 point. So this is a vector from 0, 0 to xy. The length of this vector, for example, you would have seen this is equal to x squared plus y squared. Okay, and so similarly now we can also see that you can get, so this vector, why is it u, if you want to understand. So you can think of, so let's say this point, the origin of this point is something like x naught, y naught. Okay, so if I do it this way, then what I am having is, so I can just do this. I can have a vector going from origin to this x naught, y naught. Then I can think of a vector going from origin to the tip of this vector. Okay, so if I call this as z, and this is the unknown vector which we want to show, it is u. Okay, so basically if I say okay, OA vector plus AB is equal to OB, right? This is what is called as the sum of vectors addition, right? This is what you would have seen in your earlier classes. So this is what we have, and now if I want to find out what is AB, okay, this is going to be OB minus OA. Okay, so that is actually OB. If I consider, this is represented by a vector which is, if you think about it, right, from this point to get to this point, I have to move x units in the x direction and y units on the y direction. Okay, so basically if you do the algebra properly, you will get that the vector OB is represented by x0 plus x and y0 plus y. So this will be the point B. Okay, and this is x0, y0. So in effect, AB is actually xy. So this effect of when we say we can move the same vector anywhere, okay, this is actually analogous to shifting the origin. Okay, so this you would have seen even in your analytical geometry. Okay, so whenever you have the vector, if you can just translate it anywhere, provided the direction remains the same. We have seen that that is the same vector, and the idea is you are actually shifting the origin from this to the base of this vector, and that is why this is happening. So this is not really two different views. What I would like to make you understand is that these are actually the same two things. We are actually talking about same two concepts. Okay, so this is the first thing that I wanted to convey. So are there any questions here? I hope I'm audible, right?
Yes, sir, you are.
Yeah. Okay. So this is the first point. So then the second point that I would like to talk about is the inner products. Okay. So inner products, there are two definitions that you would have seen, and it's actually quite interesting if you want to really understand why these two definitions are the same. The first definition between two vectors u and v, if you consider two vectors u and v, okay, so we will, now that you have seen that two vectors can be represented either as elements of the coordinates that they lie in, or as vectors, we can interchangeably use that. Okay, so if I assume that u is given by the vector like the coordinates u1 u2 up to un, this is one view, right? So v1 up to vn. So the inner product is defined as summation vi. So in other words, it is u1 v1 plus u2 v2 all the way till un vn. Okay, so this is one definition. The same definition, if you consider in vector notation. So basically, what we are doing, suppose this is vector u and this is vector v. If I'm taking inner product between these two, in the vector notation, what we call this as, we write this as uv cos theta, where theta is the angle between the two vectors. Okay. So this is like, so if, yeah, so let us let me give you a small example here. Okay, suppose v is a unit vector. Okay, so what is a unit vector? The mod of v is equal to 1. Okay, so if that is the case, then, so if you draw this thing, v, suppose this is u and this is v, and v is of unit vector. If I take the inner product, it is as though you are projecting this vector in the direction of v. Okay, and this is what, suppose if I call this vector as w, then w is obtained by u inner product with v. Okay, so this is like your projection operation. Okay, so the question that I would like to ask, I don't know how many of you really can understand this, but these two are one and the same, right? So these two look like completely different operations, but does anyone know why these two are the same thing? Do you understand my question? So basically, I'm saying like you have two types of inner product defined in two different ways. So one is you take this definition where you are doing u1 v1 u2 v2 and so on, and the other definition is completely geometric, right? You take two vectors u and v. I'm saying that inner product is like this, where this is the magnitude of each of these vectors, and cos theta is the angle made between the two. So does anyone know why this is same as this? If I do this, I'm actually doing this. So this is very interesting idea. Okay, so these things are some things that you can learn if you learn linear algebra properly. So for now, let us assume that this is okay. Okay, so let's just treat that these two are doing essentially the same thing. Okay, so I would have, I mean, I don't know whether these things are covered in your linear algebra, but this is something useful for you to understand that these are the same things. Okay, so this is something that is useful for us. And yeah, so if you want to learn more linear algebra, there are a lot of good resources. So the important thing is, like, if you treat linear algebra as a sequence of algorithms and sequence of disconnected ideas, then it is not a good way to learn linear algebra. It's a good way to get into linear algebra, but if you really want to understand, you have to understand a little bit of abstraction, not too much. Okay, so that way you can make these connections very well. Okay, so some of these things, some of these ideas which are required to really prove this is this things called as linear transformations. Linear transformation, then basis. Okay, then um, matrix multiplication as composition of functions. Okay, basically matrix multiplication is coming because you are composing two functions with each other. Okay, composition of two linear transformations. All these topics are something that you should know at some point. Okay, because machine learning and many things like optimization, they are highly geometric fields. Okay, so there are a lot of interesting things that you can learn by just visualizing this as like linear algebra elements. So things like PCA, which is a famous machine learning technique, is what in linear algebra the analogous thing is called SVD, singular value decomposition, and that thing is nothing but change of basis. Okay. So these things are important concepts, and as and when required, I will try to remind you of these things. But if you want to learn these things, there is one resource which I would recommend, which is NPTEL lectures by Professor Vittal Rao. Okay, so this is from IASC. Okay, so this is very nice because he teaches you not just the algorithms, but he also teaches you these the abstractions necessary. I will try to share some notes as well, but as I understand, in optimization, you are already seen some of these things. So the same things you can read up in your own time. Okay, but yeah, so these things is what I was trying to remind you of. Okay, so inner product, the takeaway is inner product in this form and inner product in this form, they are one and the same. Okay, so that is the takeaway. We will just accept it for now. You can prove it. You can think about how you can prove it later. Okay, and then another thing that we would like to understand is that this vector and the Cartesian coordinate points, they are all one and the same. Okay. So are there any questions up till here? So shall we continue?
No questions, sir.
Okay. So now the next topic that I would like to talk about is what is called as hyperplanes. So hyperplanes, you have already seen this in 2 dimensions. So in 2D, this is what is your usual lines. Okay. So what is the dimension of line? If you really ignore the the actual formal definition, informally this can be thought of as a d equal to 1. So it's a one-dimensional object, right? Because it has only it varies only in one dimension, right? So if this is a 2D plane, then line is something which varies along only one side. There is only one degree of freedom. Okay, so this is the hyperplane in 2D is a line. Okay, in 3D, this is going to be a plane. Okay, the usual plane, which is like a sheet of paper, right? Something like this sheet of paper, right? We are living in a 3-dimensional world, and this is like a 2-dimensional plane, right? So this is d equal to 2. So if I want to draw something like a plane, it will be imagine that there are 3 axes like this. Plane will be something like this. You know, it is a 2-dimensional object. So this is the plane. Okay, so we want to understand how to really understand planes in high dimensions. So this if you go on, this becomes a hyperplane. Okay, and in n dimensions, the dimension of the hyperplane will be like n-1. So this is what we would like to recap. Okay, so this is the next discussion. So now so let's try to recollect some of the things that you have already learned in your class 12 again, but because that's what will be necessary for really understanding this. So the first thing I would like to do is draw a line using, let's say there is a line which passes through 2 points it passes through 0, 3 and 2, 0. Okay, suppose there is a line which passes through these points. I would like to find out what is the equation of this line. Okay, so this will be something like ax plus by equal to c. Okay, now we know that 0, 3 passes through this. So that means if I substitute 0 and 3 for x and y, I will get 3b is equal to c, or b is equal to c by b is equal to c by 3. Okay, and in the same way, I also know that it passes to 2, 0. So then I will get 2a is equal to sorry, did I mix? Yeah, so 2a is equal to c, or b is equal to, sorry, a is equal to c by 2. Okay, now so that means so how do I find c? Can someone help me out here? It's kind of, so if I wait.
So C will just get cancelled out if we equate
Oh
A.
yeah. Sorry, yeah, that's good. Thank you. Yeah, so it's very embarrassing that I forgot this. Anyway, so c by a plus cb by 2 is equal to c. So therefore, the equation of the line, if you actually do this, it is 2x plus 3y is equal to 6. Is this correct? So let's check. So if I put
Sir, you substituted wrong actually.
Yes.
sorry, what did I do a mistake?
So
Yeah, I
C
did a
is 2 and
yeah.
C by 3.
Yeah. Sorry. Yeah. So this is a is equal to c by 2 and b is equal to this. Okay. So now this is what we get. Now, if you really so now this is one view that you have already seen. These kind of things you have already seen. Now what I would like to do is this is the analytical geometry part you have seen. But the second thing that you can do is you can look at the vector 3, 3, 2. Okay, this is a vector. So if I want to draw that vector, okay, so this is 3. In the x-axis it is 3, right? So 3, 2. If I draw this vector, so this one, if I had done the geometry properly, this vector 3, 2 would be perpendicular to this line. Okay, so though it is not very clear that's happening, but if you do it properly, okay, the vector 3, 2. So let us say that vector, I will call it as W. Okay, so W and these points on this line, okay, they are orthogonal. So what I mean is, if I take a point here, so this is one line, right? So this is a vector which is starting from O and going till A. Okay, this is the vector W. I will shift from this point to over here. So this is 3, 2. If I take inner product of 3, 2, so W times this OA, let me call this one, I will get 0. Okay, so this is another definition of the line. Okay, so you would have seen this in earlier courses, some other courses, you would have seen that W transpose X is equal to 6 is another characterization of this plane. Okay, so we will understand more why this is 6 and not something else. We will understand this more, but I just wanted to introduce that if you first, this is the view that you have in your analytical geometry. Okay, and these are the 2 points that it is passing through. Okay, and what you can do is when you solve for it, you get one form of your thing, but you can also think of these points Okay, you can think of a line by a single vector. Okay, so this is another view. So let me try to motivate this second view in the next subsequent discussion. Okay, so analytical geometric view is clear. So let's try to understand this vector view. So now the first thing that we will do to start with, let us assume that line passes through origin. Okay, so that's what we will do. So let's take an example. So let's say this is your origin, and I am saying let's consider a line which is passing through origin. And now I told you the view that we are having is, if you take, let's say this is the W. Okay, so this is defining the line, right? I told you how it defines the line. Okay, it's in the same way like this, right? So you got 3x 2y. So the same idea we are trying to learn, but this time we are doing only for origin. Okay, so now this is this W is going to be orthogonal to the line itself. Okay, and now if I take any point, so let's say there is one point here, call this as U. Okay, so this is U is given by ux, uy, the two components. Okay, so now I have already told you that you can think of W transpose U. Okay, is going to be 0, because the very definition of this other view that we are discussing is having this property that any point lying along this line is orthogonal. Any line in this any vector in this line is going to be orthogonal to W. Okay, so for points that are passing through origin, we will have always W transpose U equal to 0. Okay, so this is in one dimension. In two dimension, the line is one dimension. But if you consider higher dimension, okay, so if you consider 3 dimension, for example, you will have a plane like this. You will have some plane. Let's say this is your plane. It's passing through the origin. Okay, and there will be a perpendicular direction like this. So this we will call it as W. Okay, and every point along in the plane, so let's say there is a line like this, there is a line like this, all of this will be orthogonal to W. They will all be making an angle 90 degrees. Is that clear? So this line is like this. So every point in the plane will be orthogonal. So let me try to show you like this. So this is the plane. So this plane is passing through the origin, and this stylus here is like your W, and any line in the plane will be orthogonal to this. So suppose there is a line X here, so W transpose X will be 0. Okay, so this is the equation of a hyperplane which passes through origin. Okay, I think this is a easy concept, but just something that you need to get familiar with. Can I just quickly check if people are following this? Is this clear so far? Okay, very good. All right. So now this is what is the first discussion. Now, what I would like to talk is, like, we would like to generalize this to a line which is not passing through the origin, and then we will understand what it means in that case. Okay. So that is, now first thing is line passing through the origin has W transpose X equal to 0. Now we will generalize this to lines not passing through the origin. So let's take an example. So let's consider our a line like this in first 2 dimensions. Suppose there is a line like this. Okay, and this is your W. all the vectors that are lying here, they are orthogonal to W. That is what is the definition, right? So now we would like to understand what is the equation of this line in terms of, since it's not passing through the origin, how do we understand that? Okay, so let us do one thing. So let us take a point x0, y0. Okay, so let's say this is our point. We can call this as u0. This vector u0 is x0, y0. So you think of this as this vector. Okay, so you take any point that is passing through the line which is not passing through the origin. Okay, call that as u0. Okay, let us suppose u0, okay, is a point in the hyperplane. Okay, so now if I want to take the so now my question is, what is W transpose u0? So let us say if I want to take W transpose u0, I can actually take the same vector, assuming that it starts somewhere here. Okay, this is also u0. This also we have seen that you can shift vectors like this, and you can think that this is going through like this. This is not necessary for the discussion, but I'm just saying that you can think of it like this. And since cos theta between these two in the figure that I have driven, this angle is acute. Okay, so W transpose x0 is equal to B. Okay, in the figure, B is greater than 0. Is that okay? Because it's a when you take the inner product, what do you get? So W transpose u0 is nothing but the inner product. I hope you can understand that. So it's nothing but length of W, length of u0. So these two are positive numbers, and the cos of the angle between them. Okay, since this is making an acute angle, this whole thing is positive number. So this actually is a positive number B. Let's say that there's some vector which is B. Okay, so now I want to define what is the characteristic of any other vector x which lies in this plane. So this is x, okay, x comma y, which lies in this plane. I want to understand what is the equation of this line. Okay, so that is the next discussion. We want to derive it in a way that it is very natural and you don't have to remember this. Okay, so let's take this line. So this is a point which is x, okay, which is x comma y. Okay, and now this is W. Now I want to find out what is W transpose x. So now W transpose x, if you want, you can think of it as having two components. Okay, one is u0. Okay, so u0 and then this component. Let me show that other component in blue. So this W transpose x0 is basically W transpose u0 plus this component. Let me call this as something, let us say z. Okay, so W transpose x is equal to W transpose u0 plus z. Okay, so now that will be W transpose u0 plus W transpose z. W transpose u0, we have seen from previous discussion, it is B. And W transpose z, what is that? What is W transpose z? 0. Okay, W transpose z is 0. Therefore, what we have got is an equation of a line which is not passing through the origin is something like this. Okay, so whenever you have so this was for any point x. Okay, so this is the point. So like this, if you consider this is one point x, so any point lying along this has to satisfy this property. Okay, is this clear? So this is the equation of any line that is. So now by the way we have defined things, okay, if I take some other line W transpose x equal to 0, okay, that will be nothing but exactly same vector W will be there. Okay, but the equation will be passing through the origin. So basically these two hyperplanes will be parallel. Okay, so this is, let us say, hyperplane 1. Okay, and this is hyperplane 2. So what we get because of the way we have defined is that hyperplane 1 and hyperplane 2 are parallel to each other. Okay. So this is an interesting discussion, right? So if I take, yeah, so this is, so far I hope everything is okay. So let us try to develop this a little bit more. Yeah, yeah,
Yes.
go ahead.
That this B, I just had a doubt that if this B depends on, does this B depend on U naught?
So I have taken some U naught like this, right? But if I take some other point, let's say U1 like this, right? U1. So let us take another point U1. So Mike, you're asking, is W transpose U1 same as W transpose U naught? Is this the question, Siddharth?
So if we had taken U1 as the reference,
Yes. Yes.
what will happen to B then?
It will be the same. It has to be the same. See, because U1, okay, if you're having any doubt, so U1 is nothing but U naught plus a vector like this, right? Siddharth? So let's
Yes,
call
sir.
it W. So now if you take W transpose on both sides, okay, this is a linear operator, so it splits up. So I cannot call it W, but some vector, let us say K. Okay, so W transpose K. This will anyway be 0 because this is a vector in the hyperplane itself. So this has to be orthogonal. So this will be 0. So basically, for any two vectors, you need to have that the inner product what it makes with U0 and U1, it has to be same.
So what is this B representing?
Which one? Which one? Sorry, which one?
Sir, what does the B represent? How is it if it's invariant for a line, then?
So that, yeah, it is invariant for a line because see if you are taking this B, right, you're saying what does this B represent?
Yes, sir.
Yeah, so it is basically the inner product of any point with respect to W. That is what that B represents. You take any point you like, whichever lies. So call this as X1. Sorry, a point. Let us say P1 and P2. Okay, so W transpose P1 and W transpose P2 should be equal to B. That is what it represents.
Okay, sir. Yes, sir.
Yeah. This is like, see, this is not a new concept. You have learned what is a locus, right? So the same idea is there. So in a circle, if you take equidistant points from origin, you get a circle. So the same way what I'm saying is if you take all points, all the vectors such that they make the same inner product with W, whatever you get, that is a hyperplane. Okay. All right. So I'm assuming Siddharth is
Yes, sir.
clear.
Yes, sir. I got it.
Yeah. Yeah. Anybody else has any questions? See this you always get these lines appearing everywhere. Okay, so it's good to recollect. You might know all of these things, but it's best to yeah. Go ahead, Viraj.
So W is the vector in that particular hyperplane, right?
W is a vector which is orthogonal to these vectors that are lying in this hyperplane. Yeah.
Yeah.
See, it is important to understand two different things. Okay, so see, first of all, W. This is let me just draw a new picture. Okay, so so this is your vector, and this is W. Okay, so there are two things that you should understand. Any vector that is in this, so vector like this or this one. Okay, this is let me call this as some Z1. This as Z2. Okay, any vector that is lying in the hyperplane itself, W transpose Z1, W transpose Z2, this all will be 0. This is point number 1. Okay, point number 2 is any vector that is going from origin and whose endpoint is in the hyperplane. Okay, something like this. It's a trivial thing I'm saying, but these vectors, let us say, call this as R1, R2, and R3. What I'm saying is W transpose R1 is equal to W transpose R2 is equal to W transpose R3, which is equal to B. Okay, these are the two things that you must understand. These are not difficult things, but you must understand this in this way only. It is easy, but you might already know it, but it's good to understand. And then second picture that I want you all to develop in your mind is this. So if you have a 3 dimension, and then let us say there is a plane like this, there's a hyperplane which is I don't know whether it is going through origin or not, doesn't matter. So what is defined by is like it is having an orthogonal direction w, okay, and any vector that is lying in the plane, okay, all of those will be at 90 degree to w. This picture also I want you to develop. Okay, these are the two things. All right, so you can, so these are all orthogonal, and if you want to consider any point from origin to this, so if you consider, let us say this, so same picture that I drove here, if I draw on 3 dimension, that also I want you to visualize. Okay. All right, so let's do some more exercises so that we get to understand this well. Okay, so yeah, so let us try to do some more exercises. So, all right, so next thing. So next question that I have now is, so let's say there is a hyperplane like this. Okay, this is W. Okay, and if I take a vector like this, call this as Z. The origin is this point O. I shouldn't call it O because O is reserved for origin. So let's say this point, the origin for that vector is A. So what is the magnitude of W transpose Z? Is it bigger than 0 or less than 0? Yes. What is W? What is the magnitude? Is it? How does it compare with 0?
So bigger than 0 because it's an acute angle.
Yes. So this is the view that you should all understand. So any vector that is in this upper half, okay, will be having a positive angle. Okay. So now what I will do is let us now try to understand how do we get this vector. See, it's yeah, it may seem a little bit unnatural, but why are we doing all this? So let's take this vector from origin to that point. Okay, so let's say this is B. So OB, vector OB is nothing but OA plus AB, right? So if I take, so this was one vector OA, and then I add AB to it, this one. Okay, I will get OB. Right, so this is your usual vector addition. Like if you take this vector and then take this vector, if you add them up, this is this, right? So the effective, so this is like your force. If there is a force that takes you to this and then this, it's effectively like there is something going around this direction, right? So I mean, you might have seen this in physics. So yeah, so this is what is happening. So now if I were to ask you what is W transpose OB, okay, it's nothing but W transpose OA plus W transpose AB. Okay, now W transpose OA is this. What is W transpose OA?
B.
Yes. So what we have got, so W transpose OB is equal to B plus what is this number? W transpose AB. It's a number bigger than 0, right? This is nothing but W transpose Z, which is a number which is bigger than 0. Okay. So what we got is that W transpose OB is a number bigger than B. Okay. So what does that mean? So if you take a hyperplane, okay, something in some hyperplane like this, with your W in this direction, all these points will satisfy the equation W transpose X greater than B. Okay. In the same way, all these points, the blue points, will satisfy the equation W transpose X is less than B. The line itself will satisfy W transpose X is equal to B. Okay. So is this clear? Yes. Do you understand this intuition? I mean, not intuition, the exact proof of these things. See, this is an important concept. Okay, so these things will appear in the linear model. So I want all of you to understand this well. So can I check if everything is clear so far? Yes. Jitendra, you have a question?
Sir, I had a question, but now it's clear.
Okay. So I have noticed that a few people are not responding so much in the class. Is everything all right? See, I don't know if you know these things, but if you don't know, then it is a big problem. So that's why I'm trying to teach it. It's not a difficult thing at all, but it's something that you need to really understand well to understand the rest of the things. Okay. So let's assume that so far everything is okay. So let us do a few more things which will help you as we go along in the linear models discussion. So the next thing that I would like to do is distance between a point and a hyperplane. Okay, so a point and a hyperplane. Okay, so this is the next discussion. So let us try to formulate this properly. So there is a hyperplane. Let's say this is W transpose X is equal to B. Okay, now everybody understands how this is happening, what are all the interpretation. Everybody should be very comfortable with this. Okay, so this is the hyperplane. Let us pick a point. Let's pick this point. Call this as U1, U2. Okay. I want to find out what is the distance between this point and this line. Okay. So I want to find out this length. Okay. So now, okay. So one thing that we all know. Okay. So the idea is to find the distance between point and a hyperplane. So let us say this is the point P. My origin is O. Okay. I want to find out from the point P. I want to find out the shortest distance through which I can travel to reach this line. And we all know that shortest distance is orthogonal. Okay, so you have to take the path which is orthogonal to the line itself. Okay, so you have to go along from this point. Okay, you have to go orthogonally to this. Okay, so what is this vector? So if I go orthogonally, let us say this reaches at Q, PQ. Okay, so this is a vector PQ is in the same direction as W. Okay, so vector PQ and W share the same direction. Okay, so what does that mean? So what it means that PQ will have a form, there will be a magnitude component L, this is the magnitude, and the direction will be along W. Okay, it will be so basically what you do is if the magnitude is L and if I take a unit vector along W. So let me try to explain what is meant by unit vector along a particular direction. So let us say unit vector along W. So what that means is if you take W divided by the length of W. Okay, so any vector, you can scale it down by multiplying it by any number. So let's suppose this is a vector which is let's say w. If I do 2 times w, the vector will be the same direction, but it will go, this will be 2 times w, right? So you can scale a vector by any scalar. So alpha times w and w are in the same direction. Okay. So similarly, I can scale w by a particular number, and the number I choose is the length of w itself. Okay. If I do this, what happens is, suppose if I call this as wu, okay, this is the vector which is defined by this. Okay, the length of wu, okay, is going to be, if you want to find a length of any vector, you take inner product with itself and take the square root. Okay, so this will be so this will have right. So this will be the outer thing. If I take this out and this out, and then there is a half, so this becomes okay. So that is nothing but the numerator also is w and the denominator is also w, so this becomes 1. Okay, so if I want to take any vector, okay, in the a unit vector along any vector direction, suppose AB is a vector. If I want to take a unit vector along AB, what I need to do is I need to scale it down by the length of AB. Okay, so this is the unit. So this is the unit vector. So in the same way, what we realize is this PQ is some L times W by norm W. Okay. Is this discussion clear to people? Does anyone have any question so far? Yes. Okay. So now what we need to do, we need to find L, right? That is what we need to do. Okay. So what we will do is we will do a small construction like this. So this is OP, and OP plus PQ is nothing but OQ. Okay, so this is our thing. So OP plus PQ is equal to OQ. Okay, now we will take W transpose everywhere. What do I get? So W transpose OP plus PQ is equal to W transpose OQ. So can people tell me what is W transpose OP? Yes.
B.
No, it is not. So W transpose OP, this is just to confuse you, I asked. OP is this vector. It is some W transpose U. I don't know what it is, but you can compute it, right? U1, U2 is given to you. I am asking you to find the length of this, right? So this is a thing that you can compute. It is nothing but W transpose U, which is W1 U1 plus W2 U2. It's a number. Okay, so this is W transpose U. Okay, and what is W transpose PQ? So this is going to be W transpose with this. Okay, so this will be L W transpose W by norm W. Okay, is equal to W transpose OQ. Yes, what is W transpose OQ?
B.
B. This will be B. Okay, so therefore now W transpose W. Okay, this is equal to norm length of W square. Okay, so this will give us L is equal to B minus W transpose U, okay, divided by, so this will be W square, so this is norm W. Okay, so if you want to find the length, you can do this. Okay, and if you are only interested in the actual length and not the scale, the direction too much, you can take the norm. So it means you can take the magnitude. Therefore, length L is equal to okay. So this is why did I do this? Just to give you an idea how we can do some of this algebra. Okay, with this hyperplanes. So this is a useful concept. You must all get familiar with this. Okay. All right. So let's do one more, and then we will stop for today. Okay. So the next thing is distance between parallel hyperplanes. So if I'm having two parallel hyperplanes, what can I say about what form should it have? What are the equations? It should be of what form? So basically, if they are parallel, I know that both the normal vectors are same, right? So essentially, the equation should be W transpose X is equal to B, and then this should be W transpose X is equal to C. Okay, so any vector lying on this, if I take inner product with respect to W, I will get C. If I take the bigger one, I will get B, right? This is what we have seen. Now, what I'm asking is what is the shortest, I mean, what is this length between this? This is what I'm interested to compute. Okay, this length is what I'm interested to compute. So let us do that. So what we will do is this is, you assume that the point from where I'm taking the length is starting at x0, y0. Okay, and I know from the previous discussion, right? From the previous discussion, the length is given by W transpose. If I see this, it is B minus W transpose U, right? So this is going to be B minus W transpose. So this one I will call it as U, B minus W transpose U divided by norm W. This is the length. If I'm, yeah, so this is the length of this between these two. What is W transpose U? That I have already said that since it's lying on this hyperplane, this is nothing but C. So what I have is B minus C by norm W. So when there are two hyperplanes, if I want to find out what is the distance, this is given by this formula. Okay. So I know there was a lot of things that we discussed, but these topics are useful for future. So I am hoping that this will help you in that. Okay, so we will stop here, but I will be available for taking any questions. Okay, for otherwise, if everything is clear, you don't have any questions, then we will meet on Wednesday. No, Thursday. Okay, so are there any questions? All right, thank you everybody. So I will be hanging back for taking your questions.
So actually I had a doubt, but it was from one of the previous topics.